Right. Ladies and gentlemen, dear colleagues, welcome. I am Zdeněk Hanzálek, and you are watching the 33rd talk of the scheduling seminar. I am happy to introduce Alessandro Agnetis. He got his PhD in 1992, and in 1998 he joined University di Siena, and he is full professor there since 2001. His main research interests are related to combinatory optimization models for planning and scheduling problems and applications in manufacturing and logistics. He published many papers in reputed international journals like Operation Research, Management Science, Azure, Applied Mathematics, and so on. Okay, so please, Alessandro, go ahead. The floor is yours.
Thank you. Can you hear me? I hope.
Yes, I do.
Okay, thank you very much. Thank you for coming at this seminar. This will be a seminar on a class of scheduling problems that have something in common, as you will discover during my talk. And okay, in the first slide, you can see the main square of Siena. Siena is not a big university, but it's a place located not far from Florence, let's say, slightly south of Florence. Okay, so I'm going to talk about scheduling problems characterized by the fact that we have a stochastic element in these problems. And to motivate this class of problems, let me make let me introduce a somewhat perhaps unusual problem, which is this one. So suppose that you participate to a quiz show in which the contestant must answer a number of questions. And if question J, if quiz J is answered correctly, then the contestant wins a number of euros, RJ, given, obviously. The contestant goes on until he or she fails, and when the contestant fails, simply brings home what has gained so far. The point is that the contestant can decide in which order should answer the quizzes, okay? This was originally introduced by Kadane in the faraway 1969. So for example, suppose there is, which movie got 14 Academy Awards nomination in 1997? And if you answer this, you get 1,000 euros. What's the title of the album by Leonard Cohen containing Hallelujah? 2,000 euros. What is the name of Charlie Brown's favorite baseball player? 3,000. Which team won the Italian soccer championship in 1991? This is 5,000. And the most difficult is, what is the value of the optimal solution of Wood and Thompson job shop instance of 1963? And this is 10,000 euros. Definitely for people who are not in scheduling, this is not an easy question, in fact. Okay, so on which basis could we make a decision concerning the order in which it's convenient to, it's more profitable to answer these questions? Well, let's assume that for each quiz, there is an estimate of a probability of correctly answering the quiz. In other words, pi j, the probability, measures the confidence of the contestant in correctly answering the question. And so let's suppose that there are these probabilities attached to each question. So the question is, okay, so what is the rule or the algorithm to figure out what is the best ordering for the contestant? Well, the contestant's goal is clearly to maximize expected reward. That's the only thing that the contestant can do. So a good idea might be to choose first quizzes having high rewards, but also quizzes having high probabilities. And actually, typically, the quizzes that have higher reward also have a smaller probability because they may be more difficult and so on. So it's not clear really what is the, if you have never thought about this problem before, the answer is not that obvious, let's say. Okay, we will go back to this, but first, let me outline what I'm going to talk about in a more classical scheduling setting, let's say. We'll talk about unrecoverable interruptions. That means when a machine breaks down and there's no possibility of being recovered, of being fixed. And we will talk about both single machine and M-machine case. Then we will talk about the scenario in which these unrecoverable interruptions follow an exponential distribution. So we have exponential failure processes. And in the end, we will talk about two topics which somehow are related to this core problem. That is job replication and time-critical testing, the former being a way to hedge against failures, job replication, and time-critical testing is slightly away from this class of problems and is more in the context of testing problems, when we have to sequence certain tests, but time plays a role in it. Okay. Unrecoverable interruptions. Okay, we are dealing with scheduling problems in which machines can actually fail during the execution of a task. Of course, failure can be anything, can be a real breakdown, or can simply represent the fact that at a certain point, the machine is not available anymore because it's requested by some, for example, some higher priority process, okay? The point is that these interruptions are unrecoverable. There is, that machine is not available anymore. And what I succeeded in doing on that machine can be carried home, but from then onwards, the machine is not processing anything anymore. So, to be more precise, we have a set of n jobs, tasks, whatever, that must be processed by m parallel machines. But unlike classical scheduling, we are not sure that we are going to actually perform all these jobs, because there is a probability pi j that job j is carried out. If the machine is still working when starts performing job j, then there is a probability pi j, a success probability of successfully carrying it out. And if it's successfully carried out, we get a reward Rj. But if a machine fails, then the job which was under processing and all subsequently scheduled jobs on the machine are lost. Okay. Okay. So the problem is to allocate and sequence the jobs on the machines in order to maximize expected reward, accounting for the possibility of having these unrecoverable interruptions. So allocate on the machines and sequence on each machine. The expected reward has this expression, which is fairly simple, I think. So suppose that on a certain machine, we have k jobs scheduled. Sigma j is the job in j's position. Then the expected reward on that machine is given by, well, the first job is clearly the expected reward is the reward times the probability. Now, for the second job, the expected reward is pi sigma 1 times pi sigma 2 times the reward, because both jobs have to be successfully completed in order to get the reward R sigma 2, and so on and so on. So the last job gives a reward R sigma k with a probability which is given by the product of all the probabilities of the jobs preceding it on that machine. Okay, so finally we can define what I'm calling unreliable job scheduling problem. So there is this job set, m machines, we have success probabilities and rewards, and we want to find an assignment of jobs to machines and a sequence on each machine to maximize the expected reward. Of course, let's address problems in increasing order of complexity, and let's start with a single machine. Well, with a single machine, so one machine expected reward without any other constraint, The problem is to decide in which order should jobs be sequenced only, clearly, when we only have one machine. And this is an easy problem, because it turns out that the best thing to do is to process the jobs by non-increasing values of these ratios. So, as you can see, of course, the higher this parameter zj, this index zj, and the higher the priority of the job. So, of course, higher rewards have higher priority, higher success probabilities also have a higher priority, but the ordering rule is not simply pi j times rj, but it's also divided by 1 minus pi j. So in other words, it is the reward times the odds, what is called the odds. So pi j over 1 minus pi j. This is not a new result. As you can see, this was first established by Staggi in 1995. And so at this point, we can easily solve the quiz problem, because we compute this value zj, and then, okay, so it means that the first quiz to answer is number 2, followed by number 4, and then number 1, number 5, number 3. That's the best choice that the contestant can do to decide in which order should these questions be answered. There is an interesting point concerning the maximization of the expected reward, that there is a relationship between this problem and a classical scheduling, single machine scheduling problem, which is the total weighted discounted completion time, which consists of minimizing a weighted sum of this term, okay, where each job has a weight and a processing time, and there is a discount factor R, so that, as you can see, each job is weighted by a number which becomes closer to 1 as Cj grows, okay? And this is a classical scheduling problem, and there's a relationship with our expected reward problem, because a schedule that minimized this is a schedule that maximized the expression below. And actually, if we identify the rewards with the weights and the product of the probabilities with this summation, then we get exactly the same problem. And therefore, the total weighted discounted completion problem reduces to UJSP in this way. And in fact, the total weighted discounted completion problem is solved by ordering the jobs according to these ratios, which coincide with our ratio if we replace Wj by Rj and the exponential with the success probability. The nice fact that, of course, is very well known, but I like to always remind this, is the fact that these two problems, so the weighted sum of completion times and the weighted sum of discounted completion times, are the only single machine scheduling problems of this general form which are solved by means of a simple index rule. There cannot be any others. So one might also, well, in our problem, in our expected reward maximization problem, we don't have the time playing any role, at least for the moment. We will get back to this later. But anyhow, one might argue, let's say, okay, so there is also another category of problems which is solved by a simple index rule, even if it does not belong to any of these. No, because in practice, our problem is equivalent to the weighted discounted completion time. It's really a nice, was a very nice result by Rockoff in 1984, because he showed that only the solutions of a certain partial differential equation, the functions fulfilling a certain partial differential equation, can admit an index rule. And so, and the functions are precisely these two. So Cj and 1 minus e to the power of minus rcj. Okay, so this was just to cast the problem in terms of classical scheduling. Okay, let's make a smaller example that we will use later on with 3 jobs. So in this case, as you can see, we simply, if these are the probabilities and these are the rewards, we compute Zj, and the optimal sequence is 1, 2, 3. Okay, and here you get the value, the optimal value, which is 1.37. Okay, so on the single machine problem, there is not much else to add, to say. These are fairly classical results, let's say. But there is a variant of this problem which also deserves, in my opinion, some attention. That is, suppose now that we can only select k out of n jobs, and again, we want to maximize the expected reward. So, in other words, I've got this bunch of jobs, and out of these n jobs, I have to choose k, and then I have to sequence them in order to maximize the expected reward. Of course, once the jobs are selected, they will then be sequenced according to the Z rule, to the non-increasing ratios Zj. But the question is this selection problem easy or not? Well, one idea, the first idea that one may think of is, okay, let's order the jobs by non-increasing ratios Zj. So let's order the jobs according to this sequencing rule and take the first k jobs of the list. So in this example, for example, if we have 3 jobs, but we can only, suppose that we only have time, for example, to perform 2 of them, which jobs shall we choose? And this naive idea, this heuristic reasoning would suggest to choose job 1 and job 2, because they are the first 2 jobs in according to the Zj ordering of the jobs. Okay, so if we select 1 and 2, we have 3/4 times 1 plus 3/4 times 1/2 times 1. This is 1.12. Okay. However, it can the best thing to do is instead choosing 1 and 3, because we have 1.25. Not only, but it can also be shown that this naive heuristic of following the Z rule can perform arbitrarily bad. So it is somewhat surprising, perhaps, that this ordering rule is very good when you have to sequence jobs that have already been chosen, but it's not a good rule to actually select the jobs. Okay. Well, on the other hand, this problem is still easy, and this the way to solve this problem is actually also fairly simple, because starting from the empty set, we choose the jobs one by one, every time adding to the set the job which maximizes the marginal expected reward. So in practice, it's a greedy problem. It's a greedy algorithm, very simple. But so every time we have to try out all the jobs which have not been selected yet, and we choose the one that brings the highest benefit, the highest marginal benefit to the objective function. Again, this is a classical result by Staggi in 1995. Now, recently, a more general selection problem has been addressed, because now we can think of a situation in which each job set has a certain cost. So if I want to process a job set S, there is a cost which we assume to be submodular, and we want to select a set S in order to maximize a set of jobs S in order to maximize the total expected reward minus the cost of that set. So since the greedy approach works when we simply have a limit on the number of jobs that can be chosen, we can wonder whether the greedy approach also works in this scenario. The idea is to every time add the job that maximizes the marginal net expected reward, as long as this this marginal expected reward is positive, and then stop when there is no any more convenience to adding new jobs. Okay, this idea works as long as the cost of a set only depends on the size of that set. So this result by Olszewski and Dvora in 2016 generalizes the result by Staggi, but not that much, actually, not that much, in the sense that it only works. So the greedy approach is known, is proved to work only if it only depends on the size, the cost depends on the size. Okay, but what about a special case, which perhaps is more reasonable or realistic somehow? So each job, suppose that each job has a cost Cj, besides having a reward and a success probability. Each job has a purchasing cost, so when we select a set of jobs, we pay the purchasing cost, and then we get some expected reward, which, of course, we do not know which will be the reward. We only have an expected reward. So let's consider the special case in which the cost of a subset S is given by the sum of the costs of the individual items, of the individual jobs that we are purchasing, let's say. At least in this case, does the greedy approach work? Let's consider this example. So again, you have three jobs. Now you have success probability, reward, and now also a cost. Okay. Okay. Suppose that we want to apply this approach, the greedy approach. So the best thing to do in the first step, if you work out some computations, is to choose job 2. So if you consider the expected reward, which is 0.5 times 20 minus the cost, you get 0.11, and the same computation for 1 and 3 gives a smaller reward. However, the optimal solution is to choose 1 and 3, which gives 0.19. Okay, so the greedy approach doesn't work when we have a cost. So the greedy approach to the selection problem only works at the moment. The only case in which we are sure that it works is when the cost is proportional to the It depends on the number of items that we choose, not necessarily proportional. And it's an open problem to the complexity of this problem that I just mentioned. So there is a purchasing cost for each job, and the problem is to select a subset of jobs and sequence them to maximize the net expected reward. Okay, so this is the first open problem. I'm going to mention a few open problems throughout this presentation. Personally, I'm quite convinced that this problem is NP-hard, and perhaps it's not that surprising, but anyhow, it has never been written down anywhere. Okay, now what about n machines? Because with n machines, the problem is not only to allocate the jobs on the machines and sequence them on each machine. Okay, the problem is strongly NP-hard, even for just 2 machines. Okay, and therefore this was shown, and therefore what we can think of is to provide some approximation algorithms, possibly simple approximation algorithms for this problem. And as usual, we measure the approximation of an algorithm in terms of the ratio of the expected revenue of a certain heuristic solution over the optimal solution. Remember that this is a maximization problem, so this number will be less than 1. The closer to 1, the better it is. The first heuristic idea, very simple, very simple, is the round robin. So sort jobs in non-increasing order of the value of Zj, of the index Zj, and then schedule them on machine 1, 2, 3, up to m, and again 1, 2, 3, up to m, and so on until the end. What is the worst case behavior? well, not very good actually. With M machines, it's possible to show that the bound is, the ratio is 1/m. So we are guaranteed to get a solution which is only 1/m times the optimal value, the maximum revenue, expected revenue. A more reasonable algorithm is list scheduling. List scheduling in general is a well-known approach, which means order the jobs by criterion, some criterion, and then once you have ordered them, you sequentially assign them to the machines, also choosing the machine on the basis of a simple criterion. It's well known that for the classical parallel machines total weighted completion time problem, this is the ordering rule is a Smith's ratio, and in list scheduling, the next job on the list is scheduled on the currently least loaded machines, so the machines that has received the least workload. And this gives a classical result, the approximation ratio of 1.2. Actually, what is remarkable to say is that in 2011, a simpler proof of this result, which was very involved, I mean, the Kawaguchi and Kyan proof was quite involved, really. Schwiegelshohn showed a simpler proof of this result, and using a similar approach to the one by Schwiegelshohn, we have been recently able to derive an approximation result of list scheduling for our problem, for the expected revenue problem. Clearly, list scheduling for this problem means that we order the jobs by non-increasing values of the Z ratios, as it is quite intuitive. And the next job on the list is scheduled on the machine that currently has the highest cumulative probability. So the machine for which the product of the probabilities of the jobs allocated to that machine so far is the highest. Okay, so what is the performance of this simple list scheduling algorithm for our problem? Let me quickly review this proof, because I find it very interesting in the sense that it's an approach that gave a good, allowed to solve also the, I mean, to prove the approximation result also for the total weighted completion time. Well, first of all, it's possible to show that given an instance of the problem, the worst instances are those in which all jobs have the same Z ratio. So the worst case must be searched in this subset of instances. And if they all have the same Z ratio, any job ordering obeys the priority rule. So in this case, the ordering on each machine becomes immaterial. In particular, if all the jobs have the same Z ratio, that with no loss of generality we can assume to be equal to 1, then the reward and the success probabilities are connected, are related by this expression. And a machine's contribution to the expected reward gets simpler and is equal to 1 minus the product of the probabilities of the jobs allocated to that machine. Notice that this, in fact, doesn't depend on the order of the jobs, as it has to be. And so the expected reward is given by M, number of machines, minus the product of the probabilities allocated to machine 1, minus the product of probabilities allocated to machine 2, and so on, and so on. And we want to maximize this. Okay, and so we are restricting the sets of instances. Now we are restricting them even more, because it's possible to show that the worst case belongs to this subset of instances. Instances that contain only two types of jobs, only extreme jobs. Low-value jobs, that is, jobs having very high probability and therefore very low value, because remember that this relationship holds. And on the contrary, high-value jobs, that is, jobs having very small probability but have very high reward in comparison. And let Pmax be the maximum cumulative probability of a machine at the end of list scheduling. Okay, let's now restrict it even more. And it's possible to show that the worst case occurs when only low-value jobs are scheduled as long as the cumulative probability of a machine is larger than Pmax. Notice that the cumulative probability decreases and decreases the more we add jobs to a certain machine. So as long as it's higher than Pmax, we add low-value jobs. And on some machines, a single high-value job is scheduled thereafter. Okay, so let me summarize everything. List scheduling can produce a solution like this one. Since the jobs have all the same z-value, I might allocate first all low-value jobs, which are the small ones, and then some high-value jobs. High-value jobs completely kill a machine because their probability is close to 0. So the cumulative probability of that machine goes down. And I will never add anything else to the machine. But so the list scheduling solution can be something like this. Okay, P is the cumulative probability of these machines and of T machines, and the others have a cumulative probability that is virtually 0, as close as arbitrarily close to 0. So the value of the objective function is m minus T times P, simply. The optimal solution, according to the properties that we proved, is something like this. So some machines only host some high-value jobs, and the small-value jobs are uniformly distributed on the other machines. And this gives this value. And so, summarizing, the worst-case ratio is given by this expression, in which you find M, T, and P. T is a number of machines. And the problem is, and therefore the bound is given by the minimum of this expression for P between 0 and 1, and the ratio M over T, which is at least 1, clearly. And we can do that by numerical values. Of course, for each value of M, you can find a value. And for 2 machines, this was found in closed form. Actually, for 3 machines, just as a matter of curiosity, let me show you what is the expression of the rho, is this one. And this was found by Nicola Morandi, a private communication, who really undertook the effort of computing it for m equal to 3, and no more than 3. For m equal to 3, it was already quite complicated. And this number is, so this number, when x is given by this, is 0.86. And for any m, so the global bound is this number, 0.8531. So in other words, the list scheduling produces a solution which is at least 85.31% the optimal revenue. Okay, and that's it for what concerns list scheduling. However, on this problem, we can then try to analyze some special cases in which, for example, we have some more information concerning the failure process of the machines. For example, the case of exponentially distributed machine failures. And in this case, the situation is different because now we assume that the jobs have a certain processing time, and the reward coincides with the amount of work that we are able to carry home before the machine fails. So the reward of a certain job J is the processing time. And let's suppose that machines break down according to an exponential failure process that, as you know, has the memoryless property with mean time between failure given by 1 over lambda. And so the success probability of job J is simply this one, e to the power of minus lambda pj. So it's a special case of the problem we have been addressing so far. This is a curve that, well, this is an expression of the function pj times e to the power of minus lambda pj. And actually, the analysis revealed that there are indeed 2 subcases. If all processing times are greater than 1 over lambda, well, then a certain property holds, and it turns out that the problem is easy, solved by the round-robin rule, which means, in our case, simply okay, is solved by the round robin rule once the jobs are SPT ordered. So essentially, the list scheduling boils down to round robin with the SPT, and this is the optimal solution. Unfortunately, this subcase is not particularly interesting from a possible realistic viewpoint, because if Pj is greater than 1 over lambda, it means that these breakdowns are really frequent, right? And so we will not be able to do many jobs. Unfortunately, when that condition doesn't hold, the problem is NP-hard, even for 2 machines only. For 1 machine, clearly, it's a special case of the previous problem, so the problem is easy. But for 2 machines, no heuristic rule works exactly, and the problem is already NP-hard. That's all well, then there are also some computational results, but I'm skipping them. Okay, now in the last, let's say 10 or 15 minutes, let me talk about some ways in which we can hedge, can think of hedging against machine failure. And one possibility is job replication, which is a strategy, for example, used in the management of computer systems. That is, as a if I have several machines and some can fail, can be withdrawn at a certain point, well, if this is not expensive, one can think of replicating jobs on different machines, launching programs on different computers, for example. Because if one computer fails, maybe the program will be carried out on another machine, and one copy of each job is scheduled on each machine. And what happens now, unlike the previous problem, is that the revenue or the reward is attained if at least 1 copy of a job is successfully carried out. If 2 copies are successfully carried out, this doesn't bring me any additional value, clearly. What I'm really interested in is that there is at least 1 machine which successfully carries out a certain job. Okay, so now suppose that we have 2 machines and 3 jobs, each with its own probability, success probability. The problem becomes deciding the order on each machine. For example, if we decide for this order, which is 1, 2, 3 on one machine and 2, 3, 1 on another machine, the probability of achieving job 1 is pi1 plus, so the probability on the first machine plus the probability on the second machine, pi2, pi3, pi1, minus the product of the 2, because we must not double count probabilities. So minus pi1 squared, pi2, pi3, and the same for the others. So now this is the probability of successfully completing a job. Okay, let's talk quickly about 2 problems in this respect. The first one is maximize the expected reward. So how should I sequence the m copies of each job on each machine in order to maximize the expected reward? And how maximize the probability of having, okay, and this is a different problem now. Forget about rewards. Simply consider the probability of having a complete kit. That is, how should I sequence the jobs in order to have at least, to maximize the probability of having at least 1 copy done of each job. Okay, let me talk about the first. So the usual maximization of expected reward, but now we have to find a sequence for each machine so that the overall expected reward is maximized. So the first question is, will the Z rule work also for this problem? For example, when we have 2 machines. Suppose you have this instance, and let's consider, okay, this is an instance, let's consider the so-called identical schedule. For example, what happens if we use the Z rule on both machines? Okay, I can compute the values. And in this case, the identical schedule, so this is the identical schedule. Another remarkable schedule is the reverse schedule. That is sequencing the jobs in reverse order on the 2 machines. Okay, if you work out the computations, in this case, it turns out that the identical schedule is the best. However, if we now perturb the probability of job 3, instead of 0.6, it becomes 0.8, and the Z ordering is not violated, is the same, the reverse schedule becomes comes out to be the best one among these two. So this suggests that it's not easy to find out an easy rule. Actually, only in the uniform case, that is when all the jobs have the same Z ratios, all reverse schedules are optimal, can be shown. But if all jobs have the same value of Z, except for one, which is slightly smaller, the problem becomes NP-hard in the ordinary sense, okay? So really, this is not a problem that we can think of solving through a simple ordering rule. Its openness for strong NP-hardness. Just a few words on this problem. A simpler problem can be for two machines. What happens if we fix the order on one machine and find the optimal order on the other machine? Well, in this case, it's possible to show that the optimal sequence on the second machine, given the sequence on the first, is obtained by solving an instance of a single machine problem in which the rewards are defined in this way. Pj1 is the cumulative probability on the first machine up to job j. So a simple modification of the Z rule, or actually of the rewards, in fact, yields the optimal solution. Okay, so one can think of some using these concepts to devise some heuristics for the n machine problem with the replication, with job replication. And actually, we have analyzed 3 heuristics that I'm going to tell very quickly. So a very simple heuristic rule can be to simply sequence the jobs of each machine according to the zero. Same sequencing on all machines. Very simple, very quick heuristic, order of n log n. Well, it can be shown that this heuristic with m machines gives an approximation which is hm over m, where hm is the mth harmonic number. Okay? For example, when with 2 machines, this is 0.75. With 3 machines, this number is 0.61, and then goes down as m increases. So a better idea, inspired by the result that we've seen before, is the so-called modified Z-rule heuristic. That is, sequence the first machine according to the Z-rule, given sigma 1, optimally sequence the second, given the first 2 machines, optimally sequence the third, and so on and so on. Complexity is slightly higher because every time we have to reorder the Z values, but it's possible to show that in this way, so defining the modified Z ratios in a way that takes into account the way that all the previous machines have been sequenced, we get the optimal way of sequencing the next machine. Of course, but this is a heuristic way of proceeding, right? Because, I mean, this doesn't guarantee optimality. However, what turns out, unfortunately, I must skip some details, but what happens is that, interestingly, the expected revenue of a set of permutations, so suppose that we have sequenced k machines out of m, okay, and we consider the next machine, which is optimally sequenced after the first k, well, this function is an increasing submodular function over the set of permutations. And deciding to schedule each machine in the optimal way, given the sequencing on the previous machines, is therefore nothing but the greedy heuristic. And so this is equivalent to to finding a heuristic solution for this problem, because this is a submodular function, and the cardinality of the set of permutations is m number of machines. Therefore, as a consequence of a classical result by Nemhauser, Wolsey, and Fisher, this means that this modified Z ratio heuristic is indeed 1 minus 1 over E approximate. Okay? This is in particular a result due to Kevin Scavior. So this second heuristic is already better. Well, the last one, for which we don't have an approximation ratio, is to simply continue these improvement steps as long as there is some machine for which a schedule can be improved. So after we did everything, we can revisit the machines and see if, on the basis of how the other machines are scheduled, there is a way to improve them. The complexity of this heuristic is open, but it's possible to show that it converges in a finite number of steps. It doesn't loop because, and we stop when no schedule can be improved. Okay, some computational experiments show, this is for two machines, that the modified best reply heuristic indeed provides gaps which are pretty small. Then we also tried out a taboo search on starting from the solution of MBRH. It doesn't improve that much, but anyhow, you can see that for n equal to 2 and also n equal to 3, the gaps provided by MBRH are relatively small, especially when the interval of probabilities is relatively small. You see 0.91. Okay, last topic. Okay, an open problem, as I was saying, is this problem with replication and exponential failures. We don't know anything, not even whether it's NP-hard or not for two machines. Okay, let me skip the other, because I see that we have no problem, no time. And let me say something about testing problems. That's the last topic for the last 2 or 3 minutes. Testing problems are quite classical. We have and the problem, if you've never heard about it, is simply this one. You have a system consisting of n modular components, and the system is up only if and only if all the components are up, are working. But testing each component has a cost Cj, and the component works with probability πj. So if all the components are working, of course, I will have to test them all. But if there is some defective item, I would like to find it paying as little as possible. Because as soon as a defective component is found, the test stops. And so you will probably recognize that we are talking about a problem which belongs somehow to the same family, because the expected testing cost is given by this expression where pi is the probability that a component is working. Okay. The problem is to find the best sequence, so the sequence minimizing the expected cost, and there is a simple ordering rule. Okay, if there is a single testing unit or testing person who carries out all the tests. It's formally identical to an instance of our expected revenue problem in which we want to minimize instead of maximizing the objective function. And clearly, therefore, the ordering rule is this one, Cj over 1 minus Pj, non-decreasing values of these ratios. A similar problem is the so-called search problem. That is, an object is hidden in one of n locations and a searcher wants to find it. Again, there is a cost for searching a location and the probability that the object is hidden there. And the problem is, again, how to search the locations. Also, in this case, we have a very simple rule. What is new in these problems? And this is the last topic. Well, recently we have been addressing this problem with time constraints. That is, suppose that you have to find the defective component, or you have to find the target of the search, and you don't have much time. You have several testing or searching units that can operate in parallel, but you have some time constraint. And as soon as one of the testers detects a faulty component, the process stops. Each tester can do one test at a time. And so the problem is to assign and sequence the components to the testers so that the process is completed within a certain time t and all the tests have unit time, and the expected costs are minimized. In the search version, you have a deadline t within which the target has to be found, or and the expected costs are minimized again. So a solution is something like this. We have, let's say, m testers, capital T time slots, and in each time slot we have to decide which tests have to take place. And the assignment within a time slot is indeed immaterial. Okay, just let me give you some results on this, and then I will finish. Okay, there are some properties. Anyhow, what are the results? So the problem is how to find a partition into time slots of all the tests so that expected cost is minimum. Both these problems are NP-hard in the ordinary sense for just 2 time slots, and they are strong NP-hard. No, they are at least NP-hard, sorry, for at least 3 time slots and open for strong NP-hardness. And both problems are strong NP-hard for at least 3 testers, okay? So there is an open problem, which is the complexity of this problem when you only have 2 testers and a general time horizon T. This is still open. We don't know whether it's a polynomial or not. Okay, there would be other things to show. Let me go down to the end. Further research. Things that we have not addressed yet. Problems with precedence constraints, okay? The replication problem with exponential failures, approximation algorithms for the time-critical testing problem, and time-dependent failure processes. Okay, let me mention, these are my co-authors who have worked across several years on these problems. And okay, this is a collection of papers on these topics, and these are the answer to the original questions. Thank you very much.
Okay, thank you, Alessandro. It was quite informative. And before the others will start to prepare their questions, I may ask the first one. In most of the problems that you have mentioned, you speak about sequencing, not about scheduling, because time was not present there, right?
Yes.
So the sequence is important. On the other hand, in scheduling problems, we don't need to have sequencing always. For example, if you have parallel identical machines with Cmax minimization and use LPT algorithm, you can finally change the sequence, change the order of tasks assigned to those processors. So could you a little bit mention on how do you see sequencing and scheduling, maybe just from the terminology point of view?
Yeah, well, here in the further research, the last item that I mentioned is time-dependent failure processes, meaning that we may, well, the only failure process for which we really addressed this kind of problems was exponential failures, because of the memories property, the probability that a certain task makes it to get to the end doesn't depend on the starting time, let's say. So even if you do have processing times, in that case, the probability, the success probability doesn't really depend on the time when it starts. But we can think of different failure processes in which, therefore, for example, the probability, well, let me give you a simple example. Suppose that you are in the weekend, you have a weekend, a certain laboratory closes down, and you are told, okay, you can use the machines for yourself in this weekend, but notice that there will be some time, you don't know when, but at a certain point, they might be withdrawn from you, and you don't know when. Actually, suppose that you know that they will be withdrawn sooner or later, okay? Then, but you don't know when. Actually, you can think that there is a uniform probability across the weekend. Then in this case, the length of the jobs and when do they actually start is very important, because at the beginning, probably you will make it to do a job. But if you are in the last hour of the weekend, it's very likely that the resource will be withdrawn from you if it has not been withdrawn so far. So in that case, we have to think of a different model from this one, because the probability of having a failure does not depend only on the job characteristics, that is job duration, but also on the starting time of the jobs. And therefore, this calls for more general models to model machine failures. So I don't know if this.
Yeah. So it's related to the topic you spoke about. Okay, so now I would like to ask the others to ask a question as well. You should be able to unmute yourself. I see very famous names, so please go ahead. For example, Andrea, are you there? Okay, the second call for questions. I'm a bit nervous if I have properly allowed you to unmute, but it should work. So no more questions?
Hello.
Oh
yeah, hello Maurice.
Yes, hi Alessandro. Yes, a very nice presentation. Thank you.
Thank you.
Very interesting questions. In the case of replicating jobs, do you, I should put my video. Did you consider so when a job is completed, when one copy of a job is completed, there is no point in continuing processing the other copies of the job. So if this is allowed, then you have maybe two versions of this. There is the preemptive version where you interrupt immediately the other copies, and there is the non-preemptive versions where the other machines are tied up until the copies are finished. Did you consider this kind of variance of your problems?
We thought about that, but we didn't really analyze this problem because it's remarkably more complex than the ones we addressed, because, as you are saying, time would play a role in this case. We should know when does it happen that a certain job is completed on one machine, and then we could discard the other copies on the other machine. So I would say that this is really a more complex problem, which, however, would be definitely worth being addressed. We are implicitly assuming in our model that, let's say, the sequences are prepared beforehand and then they go, even if I might have two copies of the same job being done. But as I was saying, time doesn't play a role in our models, while in order to introduce the element that you are mentioning, we should think of an additional attribute of the jobs, that is their duration. So the answer is, I think this makes a lot of sense. So far, we didn't analyze this problem because it looks like very complicated. But let me just take the occasion to thank Maurice for one thing that you may not remember that in 2007, but you were the one who suggested me to do the analysis, the worst case analysis of the list scheduling rule, saying you might see whether you can find something similar to Kawaguchi and Kyan's bound for the weighted total weighted completion time. So somehow you also contributed to this to the progress of this research.
Okay, thank you and congratulations.
Okay, thank you, Maurice. And if there is no more question, let me thank to Alessandro, and I will inform you about the next talk in our series. It will be given by Sigrid Knust from University of Osnabrück. She will speak in 2 weeks at usual time. And thank you for being with us, and hope to see you in 2 weeks. Thank you and bye-bye.
Thank you.
Thank you. Thank you.
Bye,
Thank you.
Andrea.
Bye-bye.
Bye,
Thank
Golo.
you. Bye-bye.
Bye, Bill. Bye-bye. Nice to see you guys.
Bye-bye.